Welcome everyone to today's lecture on a very sunny winter day. It's not only sunny winter day, it's also the last lecture, the last network lecture. As you can see from this overview, next week there will be an outro from Maria, and the week after that there will be the exam. So in the remaining lecture she will give you some hints about the exam, tell you how to prepare adequately, and probably if there is something to clarify, there will also be the ability to do so. As you browse this website here, this information security page, you see that we have a log icon there. This log icon shows us that we're using a TLS connection, that our transmission is secure, that whatever we communicate, how a browser communicates with this website happens in a secured way. In practice, there's a teeny tiny fault with that. It might happen that you see this log icon and you think, wow, this connection is secure, nobody can actually listen in, nobody knows what you're actually transferring, but in fact this is a false sense of security because someone is playing around with your connection, attacking TLS, and actually tricking your browser into showing such a log icon, which signifies to the user that everything is fine, but in fact it's not. So today's lecture will be about attacks on TLS that essentially cause your browser to show such a log icon in a way that the user thinks, well, my connection is secure, nothing can happen, although some attacker is actually successful in breaking in. In the second part of today's lecture, we will only very briefly have a look at the security of DNS, and with DNS and TLS basically together, you have everything you need in order to assess the security of modern websites. So as you know very well, if you go, for example, to Graz.at, the first thing that happens if you look up this URL in your browser is that it's resolved to an IP address. So, and therefore we need the DNS. And of course there can also be something wrong. An attacker might also focus on DNS instead of TLS and eventually refer you or redirect you to another page that looks exactly the same as the one you were expecting, but in fact it's an attacker controlled version. So the purpose of today's lecture is to actually sensitivize you. You as computer scientists, you should, with an interest and idea of information security, you should be able to qualify and create the security of a website. And as you've seen last time, where we examined the security on a protocol basis regarding a certificate, regarding the cipher seeds, regarding whatever can happen if you choose, well, outdated parameters for communication security. At the same time, there are different attack vectors, and all over, once in a few months, there is a new attack on TLS or related to TLS. And depending on what type of attack, it might happen in the browser, it might be a browser issue, it can actually affect the public key infrastructure. It might eventually affect the implementation of TLS. So within a certain protocol stack, like in Apple, in Firefox, Chrome, and so on, Windows, or the protocol itself. And the idea of today's lecture is that afterwards you will have a better understanding if you see such a media report that there is a critical flaw in TLS or something related to encrypted connections has shown to be insecure, like someone could listen in although the communication was encrypted, then you should get an idea or a feeling why this happens, how this could happen, and where the flaw is located. So that's what we are going to focus today. And for a better overview, I've structured this in different attack vectors. So among them is, for example, a browser issue named SSL strip, something you will also be familiar after doing the practicals, because SSL strip is part of that. And yeah, based on that we will have a look further on what happens if a certificate authority is hacked, what happens if, or how does it look like if an implementation is actually flawed, or if there is a problem in the actual protocol. And of course, related to all that, how can you protect yourself? What can you do against such attacks? That's also where we'll look at least for a tiny bit. First, let's start with a very, very quick review of what you've heard last time, because this has already been before the Christmas holiday. No, actually, no, it's been last week, but for better understanding, let's briefly recap this. You know that TLS actually goes in between the application layer protocols like HTTP, FTP, SMTP. And if you're using TLS underneath, these protocols are annotated with a trailing S here. And the idea of TLS is actually to introduce a layer that ensures that you know who you are talking to. This is what we refer to as authentication, that you make sure that nobody can actually taint with the communication. So nobody can change even a tiny bit of your communication, or it would be detected. And of course, encryption. So whatever you transfer should be confidential. And all these services, what TLS should provide, they're essential for the communication security, but you do not necessarily technically have to use them all at the same time. So, I mean, for example, you can communicate with your bank website in a confidential way, but if there is no data integrity, it might happen that someone changes, let's say you're transferring money, someone changes the amount you're transferring from 1,000 to 10,000, and you're getting ripped off. So for that, there is a very good reason, or it makes sense to have all these services enabled at the same time, but technically TLS also runs with only a subset of it. Last week we also had a look on the handshake. On the slide you see the full handshake scenario for TLS 1.2, and you see that some of these steps were optional in case that client TLS was used. So all these, or at least some of these parts, are individual depending on what cipher suite is used. So whether, for example, with RSA a key is exchanged, so the client actually generates a pre-master secret, it's encrypted with the public key of the server certificate and transferred to the server, while with key agreement, both parties agree on a shared secret, which hopefully is ephemeral. We've also briefly spoken about certificates, but something you already know anyway. With TLS, usually it's the case that a certificate authority that's publicly trusted, that your browser trusts and the website owner trusts or the server owner trusts, issues a certificate for a website like Google or TU Graz. And since your browser trusts the CA, you will also trust this. So the trust is deferred to your browser, and your browser defers the trust to the certificate authority that has signed the certificate. And this ultimately leads to such a chain, as you can see here. In theory, you could also save as an alternative. Your browser could save, for example, the public key of every website you're trusting, but this is just unpractical and wouldn't scale. Which is why we reflect trust in such a chained way. Well, now that we know that a browser is actually responsible for evaluating this trust, eventually there might be some issues. How this trust could be actually compromised or malvertised. If we focus on the relationship between TLS and HTTP, there's always, of course, an attacker potentially that wants to access your data, exactly the one you're seeing in your browser right now. And in fact, your browser sends to the server, well, I'm supporting this cipher suite, I'm supporting that TLS protocol, but there's always something that can go wrong, and all the browsers also have to deal with legacy websites. So your browser cannot always assume that the server has the maximum of TLS security settings, that only the best settings are enabled on a web server, that it uses ephemeral Diffie-Hellman key exchange. What if a web server only supports RSA, for example? Then it's basically the responsibility of the browser vendors like Chrome and Mozilla to say, well, this is below our standards, we're blocking such kind of connections, or we're well, we're trying to get to some sort of trade-off and say, well, this is probably not the maximum of security level, but still good enough. And if you remember last time, I've shown you such a dashboard on SSL Labs with all the browsers, and you have seen an overview that all the browsers support different security settings, and not all of them are equally secure. So of course, with, for example, an older or an outdated Windows 7 installation, you get a lower security level as you can achieve with more modern systems. So, of course, in an ideal world, there would be TLS 1.3 only. That's the best choice if you can. And if you're a server owner, I'd also recommend you to, for example, use such a configuration generator where you can say, I want a modern setup. And for example, Mozilla offers such a service. If you own a web server, you can use such a tool to say, disable all the protocols except for TLS 1.3. And thereby you're targeting modern clients that support 1.3, which would mean as of 2021, Firefox in version at least 63, Android 10, Chrome 70, and so on. Very well in practice, just referring to what I just said, you also have a lot of older clients, and you, especially if you, let's say, you provide your own web shop, then you want to maximize compatibility with users because you want users to buy in your shop. So in other words, you'd probably not use the modern configuration because a lot of users still are, for example, of mobile users use something lower than Android 10. And from an economic perspective, or well, it wouldn't be wise to exclude them from accessing your website. From a security perspective, it probably would. But this is exactly the trade-off I just mentioned. So probably you might use something intermediate, and then it comes to specifying the Cypher Suite explicitly. This is what, for example, the server would offer to the client. And you see, for example, in this case, the minimum allowed protocol would be TLS 1.2. So that's, as of today, the recommended configuration for web server. You can choose, for example, for email servers from an IMAP server, for SMTP, if you provide such a service. And you might eventually get in such a situation. If you, for example, work as a software developer after your study, you might eventually need to configure Tomcats or other servers in a secure way, and then such services can be helpful. This is why I am pointing them out. So back to the attack vectors in browser. Essentially, over time, there have been evolved two most prominent attack vectors, how attackers might try to break into your or snoop into your TLS connections. The first is SSL strip, and the second one is a man-in-the-middle attack, a classic man-in-the-middle attack. And in both cases, the attacker tries to get in between what you're transferring. And in the first case with SSL strip, something you get familiar with in the practical, or as already said, the attacker can also not only see what you're transferring, but also, for example, steal your cookies as they are getting transferred over HTTP if there is no secure flag set. You've already heard about ARP poisoning. For example, the challenge for an attacker is very low. For example, you're sitting in the airport. I mentioned this example. An attacker turns on the phone, starts to pretend to be the gateway, tries to imitate the gateway, does essentially ARP poisoning, tries to become the man in the middle. You can do this even with your smartphone. You don't need any elaborate setup, so you might remain clueless. You might not actively see the attacker. And this is especially a risk in untrusted open Wi-Fi networks. So an attacker can actually, has a very low, the cost of an attack is very, very low. The other thing is SSL strip, or more accurately, it would be named as HTTPS stripping, because you would actually try to downgrade communication to HTTP in order to not having to break TLS, but in order to basically circumvent it. And last time I showed you that, for example, if you remember, I opened the browser console in Chrome and called ORF.at. And in the browser console of Chrome, you have seen that I was redirected from, I just typed ORF.at in my browser. And implicitly, if you just, for example, write a URL here, let's say ORF.at, what it does, what it prepends here on the left side is HTTP. It doesn't go to HTTPS by default. So remember last time I've shown you exactly this. What if you call a website without such a scheme? It first prefixes it with HTTP, and eventually you might end up at the HTTPS protected site, but only because they redirect you. So that's a setting at the server side, that the server sees, oh, there's an HTTP request, I'm redirecting the user to the HTTPS version. An attacker can, of course, exploit this and hook into exactly this problem. So what would an attacker do? Well, first do ARP poisoning, so to try to get in between the communication, and then if it sees, for example, the user is calling whatever website and there is no HTTPS prefixed but HTTP, the attacker could just strip any redirect to an HTTPS version and replace all the HTTPS links with HTTP and play around, or essentially be a proxy, act as a man in the middle that postulates, that presents a proxy server to the client. So again, we're not the practicals, so your practicals assignment is very close to that. And yeah, so it can, for example, happen, let's say you to go to your banking website, and even though for example, your banking website doesn't provide any HTTP version anymore, they would, let's say you go to Sparkasse, they would refer you to the HTTPS version of the website. Fine, sounds great, right? But if a user just types Sparkasse in the browser, the first attempt your browser makes to the server is via HTTP. So you might end up at something called httpbanking.com, and if an attacker is actually presenting itself as a man in the middle, that's how the attack is called, it might just play the proxy. So the attacker might just do the request himself, get a reply from the server, and strip any redirect to HTTPS. In the response it gets, rewrite any query to an HTTPS website via to HTTP. So the idea is that to whatever website the client would go to whatever website the client would try to visit, he would remain on the HTTP version. So he'd never actually get to the TLS version. In other words, the attacker doesn't have to interfere with TLS, doesn't have to break anything there, exploit anything there, because the communication remains on HTTP. What can we do against this attack from being successful? Well, two things mostly. One thing I've shown you last time, it's called HTTP strict transport security. So a server provider can, for example, say I'm sending you an HTTP header stating that for a certain amount of seconds this website must only be called via HTTPS, and your browser memorizes this. But there is a problem with that, because if this is the first ever attempt to reach a website, an attacker might just, if the attacker is already a man in the middle, might just strip the HTTP header. So for that reason, there is a preload flag. Browsers have to set and can register. But this is something I've shown you last time. There's also something else, because a lot of websites apparently don't use HSTS. So what can we do then? Browser vendors just very recently, Firefox implemented this, I think in Firefox 84, 83 or so. So in a very recent version, which is out just for 2 months or so now, that if you, for example, type a URL just like this, a server name, without specifying, for example, HTTPS explicitly, or the scheme you want to use, that they go to a secure version by default. So Firefox implemented this, and you see this article here, this news article is just 4 days old. stating that Chrome wants to do something comparable, so that the address bar should soon or may soon default to HTTPS. And if you think about it, the problem we have here with SSL strip is not new. This is around for 10 years at least. But only now, browser vendors somehow think, well, probably since most websites are using HTTPS anyway, it might be wise to default to that version, and as Firefox does, for example, only if it's not possible to establish an HTTPS connection, only then fall back to HTTP. So HTTPS by default seems wiser, and effectively would prevent this attack setting from being successful. Another attack that can be achieved, or a scenario that focuses on browsers, is a man-in-the-middle attack that involves faking server certificates. So this is now not affecting HTTP. This is now actually when we have a DLS connection, but we want to play man in the middle and present the user a certificate that's not valid. So how could this work? The thing, it works basically by user weakness. So the weakest point in this chain is the user, and effectively users often accept invalid or self-signed certificates. That's an issue that's been investigated in a couple of studies, and attackers also know about this and try to trick users into saying, well, you get an error message in your browser, but probably you want to continue anyway. And apparently a lot of users do. The other thing is that since we have at least or more than 130 certificate authorities in your browser, users usually do not check who issued a certificate. So for example, if I take whatever website, I just see, yeah, the certificate is valid. And then I see, oh, okay, this website is using a certificate from Let's Encrypt. That's the CA here. But usually you do not check. You go to your website and you think, well, I see a lock icon, that's it. But you do not check who issued the certificate. So what if a certificate authority you've never accredited, the website owner doesn't know about, has issued a certificate, for example, google.com. Of course, your browser would trust it because it trusts the certificate authority. What makes this even worse, or where this is even worse, is with mobile applications. Because usually when we're using, well, most of the time we are spending in our browsers, we have at least an address bar, and we have at least a theoretical opportunity to check here what we trust and by what settings. What if you open the PayPal app on your phone or any banking app on your phone? Actually, there is no way for you to see whether the application actually uses HTTPS or why it uses TLS basically underneath as a protocol. You have no way and no idea. And there are still a lot of apps, luckily less meanwhile, but a few years ago it was more than 30%, who did the communication over HTTP, and users had no chance of noticing, because there was no. And usually you have no address bar in apps unless it's a WebView app which shows you the address bar, but usually you have no idea. And a lot of applications also skip certificate warnings. They implement their own trust managers. For whatever reasons, the default setting would be secure, but apparently a lot of applications are overriding these secure defaults with their own implementations and actually making the world less secure. So that's still a thing. And how does it work? Well, the client, as it would be secure, as it would be important, just request a page via HTTPS. The attacker then just copies all the attributes in the original certificate and presents a fake certificate to the browser and pretends that this is legitimate and hopes that the client will accept it. Of course, if the client does so, the attacker also has all other abilities to interfere with the communication, not only listening in, the attacker can also change content, inject JavaScript, keylogger, and so on. So this is where you're doomed if the user actually would accept this. And how does this attack work? You'd basically just use any tool that's publicly available, like SSL Split, man-in-the-middle proxy, Fiddler, Burpsuit. This is a compilation of the most popular ones. And what you see in the screenshot is, for example, here, this is from a tool called SSL Split. You see, for example, the user apparently, there's a man-in-the-middle attack going on. The user called facebook.com. SSL Split sees this, does communication to facebook.com, and then generates its own certificate. You see it here in the red, in the box, the red border. Here it says forged server certificate. It just imitates all the attributes, the subject, the common name from the original certificate, but you can see its fingerprint is different. So this is a self-crafted certificate, which is then shown, which is actually sent to the user, or which the attacker presents to the client throughout the man-in-the-middle attack. And SSL Strip is highly automated, so this works for whatever website is called. You don't have to do anything manually here. This is fully automatized, so eventually the user might not even notice, or he might just say, yeah, continue. Or if an app, for example, using a mobile app, and the app doesn't warn about self-crafted certificates, then you wouldn't notice at all. And if the attack is successful, you will just see the plain HTTP communication, although it's actually over TLS. So in fact, how the attack scenario looks like is shown on the picture on the left bottom here. When the attacker, for example, in this case, it would be exactly the same scenario with man-in-the-middle proxy, just a man-in-the-middle attack, and the attacker would just present fake certificates for whatever domain the user would call. So, of course, browsers try to protect against this. If you go to a website where this happens, it shows you see an alert. You see a box like the one you see on the screenshot here on the right. It says, hey, this is insecure. The HTTPS is crossed out in the address bar. You should not continue here. We are warned. It seems counterintuitive, but apparently a lot of users can try to or intend to continue anyway, because apparently getting to a website very often has more relevance than considering security warnings. That's a cruel fact, and studies have shown that this is the case. So the numbers I've linked here in the slide are from studies done by Mozilla and Chrome, and they got these numbers throughout their telemetry programs, which they implement in the browsers, so that they see how users actually use the browser, how to monitor the usage. And apparently before they changed these dialogues here, so that actually there is a two-step verification. The users have to click on this advanced button here and say, yeah, I want to continue anyway. Apparently 70% of Chrome users, for example, continued anyway. So only by this extra step, which they introduced, where users have to click in addition, reconsider another time, this somehow lowered these numbers, and eventually they might be lower meanwhile. But yeah, this is a thing. Users just click away these dialogues. And unfortunately, even regular servers very often show invalid or expired certificates. So especially certificate expiration is a very common thing. It also happens here at the university, that you, for example, you go to Online til Granskate, and eventually you see such a warning. And it doesn't always need to be the case that someone is attacking you. It can also be just, for example, that the certificate expired, nobody renewed it before the expiration date was reached, and then you have the chance on whether you continue anyway on a potentially untrusted connection, or you'd better call the TIT and tell them, well, something happened. And this is especially cruel with ministries, with airports in Austria, which suffer from the same thing. So even with legit site, there are often issues that so that users know, well, there's an issue, but let's step over it and go to the website anyway. Another type of attacks relating to public key infrastructure. So you've heard about this last time. What's the purpose of a PKI? It's ensuring trust, of course. It's responsible for checking the identity of who wants a certificate, for being something like a passport issue to a web browser and to a server owner. So the problem is, or what is trust in that context? We already had this last time, but just to recap this. We have a trust chain, so certificate authorities can defer trust to so-called intermediate certificate authorities. They can say, well, you do not have to request all certificates at our place. We are deferring some responsibility and tasking some intermediate CA, some next certificate issue in the chain to say, well, you're also authorized now to issue certificates. And all the browsers what the browsers do is resolve this trust chain, go up from the server certificate throughout the intermediate certificate up to the root certificate authority, which is stored in your browser. And if it sees this, then the browser assumes this connection has to be secure. So by that, this means that any kind of root or intermediate CA decides what is trustworthy. And besides these, among these 130 certificate authorities in your browsers, a lot of them actually belong to different countries. And the EFF organization built a list of if you just check the list of CAs in your browsers, if you're curious, and you will see that for a lot of them you don't even understand the name. And you have no idea to what country it belongs to. It contains a minimum of information about who issued this CA, who is the owner of it. But apparently, at least 46 CAs belong to the government of different countries. And unfortunately, not all of them are equally, secure or trustworthy from a Middle European perspective. Apparently, your browsers trust them anyway, because somehow they got included there. And in addition to that, a lot of companies have intermediate CAs which also allow them to issue certificates for whatever domains they want to. For example, the Department of Defense in the US, Department of Homeland Security, Booz Allen Hamilton, observatories, Dell, Ford, Google, Marks and Spencer, Vodafone, they all can issue certificates for whatever websites they want, because they have their own intermediate CAs, or Google also, for example. And if you do not explicitly check who issued the certificate, you wouldn't even notice if this is suddenly another issue, unless you use public key fingerprinting, public key pinning. Remember last time there was HPKP, and I've also pointed out that barely anyone uses this in practice because it's highly complicated to configure, and a lot of things can go wrong. And if you do it the wrong way, then you might block out users forever from accessing your website. So what can go wrong here with PKIs? The thing is that basically any certificate authority can issue any certificate for whatever website. So in other words, they do not have to ask approval from a domain owner from out there self. And very often, if you request a certificate for a website, the validation that's required by the CA is very weak. So very often, for example, it's just so-called domain validated certificate. In other words, you're getting an email, then you have to click on a link and say, and they assume if you control an email address, for example, webmaster@domain.com, then you might also have control over the domain. This is not necessarily always the case, and it also led to problems in the past where people were able to request certificates for websites they had no factual access to. The other thing is that revocation is in fact broken. So there is something called certificate revocation. You've already heard about this, and the idea is that all the CAs provide servers, either with that present blacklists with a certificate revocation list or a so-called OCSP responder. In other words, services that tell your browsers if a certificate has been revoked. So in other words, declared invalid. For example, because the private key was leaked, or whatever other reasons. In fact, in practice, this is just broken, because you have probably never seen your browser from failing to access a website because a certificate was revoked, or because the OCSP responder said, well, no, I don't want you to use this certificate. The reason is that all of them implement the so-called soft failing. In other words, if they don't get a response from the server, they just ignore it and continue anyway. So let's say you go to Google.at. While you do so, in the background there is, as soon as, for example, as your browser receives, let's examine this. So for example, I'm going to Google.at. My browser loads a certificate, and in there is a reference to an OCSP responder to a server. And my browser in the background checks whether the certificate the server just showed me is actually been revoked. But if this actually is the case, or if it doesn't get a response, it just fails silently. If as an attacker, you would just block the response, and then the client would never notice. There's also nothing in between, so your browser never trusts a server partially. It either trusts it fully or not at all. So this means lock icon or no lock icon. And the only thing that's in between is probably a mixed content statement in Firefox, which would show you a yellow triangle, but this is not really related to TLS. It's more related to mixed content, HTTP and HTTPS mixed. So it doesn't affect PKI or trust here. What can also happen, and happened a few times, is a so-called root key compromise. In root key compromise, a certificate authority is actually attacked, and attackers try to extract private keys from hardware security modules. Such a hardware security module can look like the one you see here on the top right. It's basically like a box in which you generate secure keys, and the idea is that all the encryption, decryption is done inside that box, and that the key can never leave this tiny box. So it's protected, and also physically strongly protected, and even if this box is disassembled and someone tries to extract it, it shouldn't be possible. So stealing them from such boxes is comparably hard. But as always, it might happen that there is a flaw in the firmware, or someone gets access to it, and can still do it what should technically not be possible. It can also be that, for example, a government, for example in the US, there is just a governmental letter to the company and says, well, we need access to that. Give us the key. And then they will say, well, we have no ability to do so. But sometimes they are not as honest as they claim, and in fact they have the keys or can extract them. So in a lot of cases also, if you provision such an HSM, you have to do this the correct way. You have to, for example, say the key should be non-extractable. But if you set the flag that it is extractable, then in fact you can read it out, although that's not the idea. In the past, people or attackers actually circumvented this and aimed for something else. So instead of just extracting the key, they thought, well, let's make the CA do whatever we want by simply hacking it. It happened already in 2011, but this is very well described and a very well verified example, which is why I'm bringing it here. In the past, there was a CA called DigiNotar, which was hacked, and this became public or known because a user from Iran actually wrote in the Gmail help forum stating that from some time to time he cannot access the Gmail service. And later on he said, well, just on a daily basis from 30 to 60 minutes he was unable to reach the page, and he realized this is some kind of attack. So he here stated, I think my SP government did this attack. The reason he noticed is that Google back then already had HPKP, the public key pinning, installed, and in the downtime, when these 30 to 60 minutes, when the user could not reach a Gmail service, HPKP actually was effective apparently, and deferred this attack. So what happened? In fact, the entire CA was hacked, and it became known that all the servers that were responsible for issuing certificates were accessible from over the management LAN, and apparently attackers had access to the management LAN, so they could also instruct the issuance server to issue certificates. They were members of the same Windows domain, so they were also not physically or organizationally separate. The password was apparently weak, the admin password, and they just brute forced it. More than that, the web server software was outdated, not patched. There was no malware protection or anything installed, and why it was probably even harder for them to verify an attack was going on. There was an intrusion prevention system, but no central logging instance. So a lot of fails here, and all this together apparently contributed to the fact that attackers had an admin account, a Windows domain admin account, which they could use to issue certificates for arbitrary websites. And they did so on a wide scale. For example, they issued more than 500 certificates for very well-known websites, among them, for example, Facebook, Twitter, Google. And besides these domain-specific certificates, they also issued certain wildcard certificates here. So what you see here with this **.*.com, this is so-called wildcard certificate, which you can use for any com domain. So this asterisk just will be, so for example, the *.google.com will work for any subdomain of the google.com, and this certificate will work for any com domain, that one for any org domain. So that gave the attackers a huge range of domains where they could hijack they could present the certificate to browsers, and they would happily accept it. And while many certificates hacked by this authority were fully valid, they were actually issued by the CA. Some years ago, there was a malware that produced cryptographically valid certificates that were not signed by CA. So it's now a different approach to that. And that's the approach that has been followed by a malware called Flame. And I'm showing you this example because it's quite counterintuitive. Because how can a certificate be valid if it wasn't signed officially? So if there wasn't, here in that case, the attackers had access to the HSM, to the CA, and they could actually sign certificates the browsers would trust. Why? Because they would trust the DigiNotar CA. So someone just hacked the CA. But how can a certificate be valid if it's not officially issued, not officially signed by a key their browser trusts. Well, let's have a closer look at how this worked. The Flame malware was very advanced, and there are rumors that it can originate from the Israeli intelligence services. It's found to be used in several Middle Eastern countries, like especially Iran, Sudan, but Israel was also affected, so probably they are not the authors of that malware. It's been active for 2 years. It's fairly complex. There were more than over 20 attack modules that can be used for network sniffing, for enabling the microphone, for retrieving whatever files, and so on. And apparently it shared code with another malware called Stuxnet. Probably heard of that. It was an implant that's been placed into Iranian nuclear reactors, and also rumors that Israel is the author of that. So the reason I'm presenting is that it used a valid certificate that was not signed by CA. How did this actually go or come to computers? That's also an interesting thing. So assuming a computer is infected via USB stick, how would you actually proliferate the malware to other hosts in the same network? And Flame used a very clever trick for that. On Windows computers, there's a service that's running on all of them, which is the Windows Update service. So why not distribute malware as a Windows Update? Or trick computers into believing, well, I'm contacting this host anyway, so let's retrieve what it's actually sending me. So how do you do that? They used a clever trick. They got the hosts to download the update from an attacker server by pretending to be the Windows Update server. And they did so by crafting a so-called Web Proxy Auto Discovery Protocol file, a so-called WPAD. This is something in LANs very often used in order to tell a host, well, we're using a proxy, there is no direct connection. So you set up such a file, and just for demonstration purposes, I've here listed this, how you would do this. This is just simple JavaScript, for example, or very similar to that. You'd say, for example, for any host in this, the example.com or any subdomain of example.com, you would not use a proxy. For anything in this private network here, you would probably route this over my proxy, or any other request would probably go over the proxy or directly to the internet. So this is a file that's often, if you just turn on Wireshark, if you're curious, and you will see that your Windows computer very often or in regular intervals will poll for such a file. It will poll via DNS, DHCP, NetBIOS. It will try to, if there are other hosts in the network, it will try to receive such a file from other hosts. And if it sees it, it will configure the local computer to use a proxy if there's the automated configuration of proxy servers enabled. So that's exactly how this malware spread. Because they waited until another host in the network did such a request for that file, and if it found so, it would just set it up. And for whatever request to this update Microsoft.com server, it would then go over the attacker's host. So how could you do such an attack? Not only this malware, but it would also be easy for you. You just have to set up a fake DHCP server that presents such a WPD file, and that's malicious or that's been crafted by you, and they would say, well, for any request to the internet, route this via me. So that's some sort of man-in-the-middle attack without op poisoning. Now what happened if hosts received this file? this file included a statement saying if a host wanted to go to the update Microsoft.com server, it should route the traffic via the attacker's host. Now, as you know, that Windows computers are polling for updates on a regular basis, it happened that all these hosts in the network just asked then the attacker basically, do you have any updates for me? And in the case of this Flame malware, the attacker just said, yeah, I do. And this is where they presented the malware. Unfortunately, what made this attack even easier is the fact that although the update service from Windows uses HTTPS, for compatibility reasons with all the devices, it still, even as of today, supports communication over HTTP. And of course, to make sure that, well, not any kind of updates can be downloaded from that service that are potentially fraudulent, like in this case with the malware, there is so-called cold signing certificates. So apparently Microsoft has to sign all the updates and the computers are advised to check them. The problem in this case, why this attack worked, is that MD5 was used. And you know MD5 already. The hash mechanism that's been broken for years. And it was easy to find a collision, to build a collision. So the attacker used an attack on MD5 to create a valid certificate. It was cryptographically valid. In other words, the attacker signed the malware with its own private key, but the signed MD5 hash, it used the signature was just fake. So the MD5 hash and the signed MD5 hash was just the same as from the original update. So in other words, the attacker tricked or found a collision and tricked the host into accepting this. So not the key for signing was broken from Microsoft, but the attacker exploited a vulnerability in the signature algorithm. So the attacker now has only changed the public key, the signature and the hash value actually remained the same, and this is why the hosts actually trusted this update package. And this is how they spread the malware to other computers. So overall, as a result, the hosts are presented with a cryptographically valid certificate. So this is the content of certificate, this Microsoft update Microsoft.com certificate. It was cryptographically valid, but it was just never really issued from Microsoft. And the same thing could happen to SHA-1. And if you have followed the media reports over the last years, you know that SHA-1 is now banned or sort of banned from browsers because researchers have found serious flaws in that signature mechanism. So with MD5, it's now very, very cheap to calculate, to compute, to find a collision. With SHA-1, it's also possible. That's the reason they have excluded this from browsers. So what can we do to make such kind of attacks harder? So of course, among them, there's public key pinning. For example, what you have heard last time, you would instruct the browser to remember the public key of the certificate, and if it sees another one, it would just not allow the communication. Then there's also something called DANE. DANE is based on DNSSEC, something you will still hear about today. It's some sort of pinning, but you do not, instead of with HTTP public key pinning, you send the pins in the HTTP header. With DANE, you would just store the pin as a DNS record. Another approach, that's probably the one that will in the future become the major one to deter such kind of attacks, is called certificate transparency. With certificate transparency is a framework, an online framework that monitors issuance of certificates. So for example, Google was a main driver behind that, and they say that for whatever certificate that should be accepted by Chrome, we require it to be listed in the certificate transparency framework. And for example, just to give you an idea of how this works, for example, there's you can publicly browse this. Oh yeah, here we go. For example, you can say can take some time, and the result will be a list of certificates that's been issued for TU Graz AT. Not the fastest site. Oh yeah, there we go. Yeah, so let's pick one here. You see, for example, that the CA Assign issued a certificate for that domain name, for our institute, by the way. Oh, with a very weak with a very weak RSA key, but that's been 10 years ago, so this is already a long time expired now. Back then this was considered secure. So, and if you call a domain where in Chrome, it will check this directory on whether there's an entry for that. So the idea of that is, if you see, for example, a certificate for google.com or whatever domain, and you don't know if this is actually, from some government domain, CA or so, or actually from the real issue of Google, you could check this log file and see who issued the certificate, where there's also an entry here. And just as a side note, if you're curious about, for example, what subdomains are there actually existing for TU Graz AT, you might also just use this tool. And this is quite dangerous because all attackers, for example, use this to, if they have a target, for example, some domain in the critical infrastructure, to see what subdomains are existing for that and then try some attacks on that. Just as a side note. So that brings me to implementation attacks. That's another category of how you could attack TLS. So the problem is very shortly explained. The thing is that those who design a protocol or a cipher are very often not the same persons who implement it. And if these persons who implement it are not savvy enough to consider all the security critical aspects, then something can go wrong. And breaking crypto is usually always harder than just bypassing it. So if you don't have the computational resources to break something, just try to bypass it. And you can do so, for example, by just installing another root certificate and then issuing certificates for that, using that root CA. That's a very, very smart way of doing it, or bypassing it. Or you just exploit some certificate validation flaws. For example, verifying that a certificate is entirely valid can be challenging, can be difficult, and a lot of things can go wrong there. So to give a better understanding of that, let's look at some examples. In the past, there was an incident called Superfish, which was a certificate, a root CA, that was pre-installed on all the Dell notebooks, or a majority of Dell notebooks, and it also became known with Lenovo and others. They essentially installed a root CA called Superfish that analyzed images on web pages and provided matching ads. For whatever reason, I don't know what drove them, but of course such a CA that was pre-installed could issue a certificate for Google for any other website. And while you might think, well, this is Superfish, this is just one example that's already old. In fact, if you're right now, for example, using a Windows computer, and you're using a so-called premium internet security firewall like ESET, Fortinet, Symantec, then chances are very, very high that they installed their own CA on your computer. And they are actually breaking the communication of your browser and the server and trying to get in between. So that happens in a lot of cases, especially these so-called antiviruses, ad blockers, adware protection mechanism software, they do so quite frequently. And so how would you see this? For example, in the case of Superfish, you would just explore, you would have a look at the certificate manager and you'd see such a record containing Superfish. If you are on Windows, you could also check the certificate manager of your computer and you would also see this installed here. And by the way, if you're using ESET or so, you would see, as a trusted root certificate authorities, you would see something called ESET SSL filter CA or so. So the problem is, ESET, Avira, Kaspersky and others, they generate their own certificates, install them there, and then sniff into, so they play the man in the middle by generating separate certificates for each domain you call. The problem is very often they also, well, they don't, for example, they don't support TLS 1.3, they only support TLS 1.2, weaker algorithms, weaker ciphers. So you actually weaken the security level of your communication. And sometimes they do so in a very drastic way. So that this means a serious connection downgrade. Another thing that can happen is simply when certificate validation has a flaw. And this sounds so trivial because, well, when does your browser, we already had this last time, when does your browser trust a certain certificate? Well, of course, the first thing it does, it checks whether the domain name it sees here within the certificate issued to, whether this corresponds to the name in the address bar. So good, so well. Then of course the certificate is still valid, that all the signatures are valid, that we know who issued the certificate, and of course we also verify each intermediate certificate, and then we should be good to go, right? In fact, a lot of things can go wrong. The devil is in the details. Of course, when developers develop this, they test it with certificate chains defined in real life, but they will never be malicious and designed to subvert security. So as a result, it isn't uncommon that developers miss some critical checks. And if you're interested in how to do this properly, I've especially placed a link here which will lead you to a detailed report on what you have to consider in order to verify such a certificate chain in detail. And of course you don't have to learn this by heart, how to do it correctly with OpenSSL, but this is just to illustrate you how complicated this can be and what can go wrong with that. And this one also underlines or explains to some extent how such certificate validation flaws can actually emerge. And among them, for example, this is just an example I've picked. There are countless others that essentially have the same thing, but this is a high security bug, a padding oracle, and a memory corruption threat, which we found, for example, in OpenSSL. So, and the description sounds quite alarming. If you read, for example, the implementation of OpenSSL allows remote attackers to execute arbitrary code or cause a denial of service via any field in crafted serialized data. So this just as a symbol to what happens in countless libraries that are used for certificate validation, like OpenSSL, GNU-TLS, the Microsoft Crypto API, that there are flaws in there like padding oracles or memory corruption. And another flaw that's been explored in the media very widely is called Heartbleed. Heartbleed is a so-called information disclosure vulnerability in OpenSSL, and it was named Heartbleed because it exploits a fault implementation of the so-called Heartbeat protocol. This Heartbeat protocol is barely used, but it was enabled by default in the so-called DTLS service. How did it happen? Developers simply forgot to check the length of an input variable. And this allowed an attacker to simply request up to 64 kilobyte of code in the process memory. And if this was exactly in the memory, for example, a private key or something sensitive, then this might get leaked. So the response could simply include session cookies, passwords, private keys, and you could also try to get this out. How did this happen? Why was this in there? The reason was simply that the code in OpenSSL is bad quality. So if you're curious, go to GitHub. The source code of OpenSSL is of course public, and you see that it's an awful quality. It's been audited a few times. OpenSSL then ordered these audits after Heartbleed occurred. Some people thought, well, such crappy software can't be secure, so they made their own forks like LibreSSL, but in fact OpenSSL is still the standard we're using. And I don't say it's unsecure, but bad code quality of course promotes the existence of such critical flaws. And there will be in future more problems, more serious problems with OpenSSL as we had in the past, and which is why it's important to always also update the OpenSSL library if you're developing such software. Another thing that's become very popular, which I'd like to show you an implementation flaw, is called go-to-fail. It happened in an old version of the iOS operating system, and since iOS and macOS are using the same protocol stack, the problem also affected macOS. So what happened? In fact, in the code that was used to verify the handshake, the TLS handshake, they missed some brackets here. So in this if, they just copied, for some reason they copied this go to fail statement here. And because of the indentation here, you don't see the bug immediately, but essentially it skipped the SSL raw verify, so the intended signature verification was never done, and in practice this meant that the implementation just skipped the server key exchange step. So this would allow any private key from being accepted. This means I can show any certificate from, for example, from Google, and can take my own private key, and the implementation would still accept it. So this made it possible, for example, to send a correct certificate chain to the client, but sign the handshake with a wrong private key, or not sign it at all, and the check would never be done simply. So yeah, thereby this makes SSL or man-in-the-middle attacks a lot easier, because the client would never show any warnings about untrusted certificates. Another thing, more recent, just a year ago, was a critical Windows 10 vulnerability and this is exactly the example I've shown you in a browser, that as not always when you see a lock icon it means you're secure. So what happened? The NSA actually found a certificate validation bug that concerned ECDSA signatures, and it was based on a spoofing vulnerability. In the Windows Crypto API that's used, for example, by Chrome and Edge to validate elliptic curve crypto certificates. So in ECDSA, you know that the private key is a large integer, while the public key is a point on the elliptic curve derived from some derived from by computing, for example, for a generator of the curve with a large prime order, right? And in this case, when the vulnerable Windows versions check 3 ECC parameters, they fail to verify a fourth. And that's the crucial one, because it's known as the base point generator, and it's often represented in algorithms as this G prime. This is a failure, simply the result of the Microsoft implementation. So when implementing this, Microsoft simply did a crappy job. And this is no flaw in ECC itself. It's just that they forgot to verify some parameter, and this enabled an attacker to just spoof trusted ECC root certificates by crafting valid private keys. Therefore, they just had to copy an existing public key and all the certificate parameters, and the implementation just didn't check whether the private key is valid, because they missed to validate some parameter here in the implementation. By the way, this bug worked, or this implementation flaw was existing for 5 years. So the NSA found this, and they basically had this open for 5 years. They found it in July 2015, and it was fixed by Windows Update in January 2020. So that's horrible if you think what might have happened in between, in the time frame when this bug was not fixed yet. The last attack group, the group of attack vectors I'd like to speak about regarding to TLS, are so-called protocol attacks. So over time, different protocols have emerged of TLS, and with them also different attack scenarios. And they have over time retrieved some, some famous names like Beast, Crime, Breach, Freak, Poodle, Logjam, Drown, and they're all affecting different protocols. And for example, this Drown attack here referred to SSL version 2, which was back then still enabled on a lot of servers, and this led to the disabling of abolishing SSL v2 entirely. Poodle, for example, made it obvious that SSL version 3 is broken and led to SSL version 3 being banned. And this actually continues. So this is just an excerpt where you see that it's not only plausible, it's almost certain that new attacks will come up, and that protocols will have to get outdated and updated, and we need newer ones that are more secure. So how did these attacks basically work? I've tried to categorize them to get them to find a way to see on what attack vectors they are based upon. So on the one hand, we have downgrade attacks, which try to, for example, bring a TLS 1.2 connection back to an SSL version 3 connection. Then there are compression attacks, which try to figure out what you're actually transferring. Then padding oracles, mostly on CBC mode. RSA related attacks like the Bleichenbacher attack is very well known, or something called insecure renegotiation. So especially with downgrade attacks, this is very easy to get what it does. The problem is, or why this works, and this brings me back to the beginning of today's lecture, I told you that web servers and browsers have to also be, or very often there is a demand to be compatible with older clients. So this also means that for compatibility reasons, often weak ciphers remain activated. And attackers could try to trick servers and client into negotiating connections using them. So in other words, downgrade an actually secure connection to an insecure protocol or an insecure cipher. In 2014, there was an attack that's called Freak, factoring RSA export keys. And the idea is quite simple. It's based on the man-in-the-middle attack, where the list of supported ciphers is simply swapped by a few of them that are marked with a keyword called export, so-called export ciphers. And you might wonder, what is an export cipher? Just a quick story on that. In 1991, Phil Zimmermann presented the PGP encryption solution, and the NSA was afraid that they could not break it. So in 1992, there was a deal of the NSA with the Ministry of Justice in the US, and they say that for whatever products that are getting exported worldwide that include crypto, they must not be stronger, they must not feature more than an RSA key with 512 bits or a 40-bit ARC4 key. So in other words, they actively promoted weak crypto because anything stronger they could not break anymore. And this led to the specification of so-called export cipher suites, as the ones you see here. And if you remember last time I showed you a command, I cannot execute it here in Windows now, but if you have in any Linux, you can do this. This is the command I've shown you last time. And it will show you a list of supported cipher suites, and among them we will also still see these export ciphers. So how does it work? There's a man-in-the-middle attack going on. The client actually supports probably secure ciphers also, but throughout the man-in-the-middle attack, the attacker simply swaps these exports, swaps the secure cipher suites by export ciphers with a weak key, goes to the server. The server unfortunately still supports these weak cipher suites. Not all of them, of course, luckily, but there are unfortunately servers which still support these cipher suites. And this means effectively the communication was downgraded. In fact, in this scenario, the attacker performs the attack in a way that the client doesn't notice anything, because the export cipher is supported. So this is simply swapping something but not breaking it. And for an attacker to brute force these keys, this can be cheap. So the hurdle here, the client doesn't notice anything. For the client, it seems like a valid connection. The man in the middle just swaps the supported ciphers with the export ciphers, and then the attacker cracks the export key. That's it. Another type of attack, on the second category of this protocol attacks, is a compression attack. And this might remind you of something you've already heard throughout this lecture. The problem is, if a server applies compression on encrypted data, an attacker might try to figure out, might try to add something which is then also compressed. And as you know that, so how does compression work? Usually, in most settings, you have each character only once, and then some efficient tables that say, well, this character is used this and there. So based on the size of the compressed content, you get an understanding of what is compressed. So in other words, if you add something and the compressed content is not increasing, then you know that the character or the bytes are already there. So in other words, this is like an oracle, a compression oracle. An attacker can guess what content is transferred within the encrypted message. What does it mean in practice? Bullshit bingo. We're trying different characters and see if they're already in there. This is an attack, an oracle. To make it more visible, quick example. Within a compressed data, you can have, for example, a statement like this one: if you can't forgive yourself, how can you forgive someone else? So if you compress this, of each of these words, you'd have only one copy. Such a padding or a compression oracle exists if an attacker can add data, and then it's compressed in the same way. So for example, let's say there is such a request, like the one in the example on the left here. The attacker just, at some point where it guesses that this might be the location where there's a session ID or so, in this case, for example, the attacker guesses a session ID, tries to, for example, insert an X here, and if the original message did not yet contain this X, it will be noted as an incorrect, so the guess will be incorrect. Why? Because this X will also be compressed and the overall message size will just increase. The compressed content size will increase. Otherwise, if the data is already there, for example here, where the attacker wrote B instead of X here, and the size stays the same, then we know that, so apparently we have guessed something that's actually in there. And this may seem quite dumb with single characters, but you can also play it with entire strings. So instead of only one character, you can take entire byte sequences and try to see if they're in there. So this is a so-called compression attack. What do we learn from all that? Of course, first of all, certificate handling, parsing, validating is hard to implement correctly, and I really recommend you to check out the link where I've hinted about how to do it correctly, and you will get an understanding of what implementations aspects are crucial for that. And if you ever implement such a software, I mean something related to verifying, to validating TLS certificates, you should strongly stick to guidelines or libraries that are well tested and where there is a very high chance that it's done correctly. So doing it yourself is very often very risky. And as always, before breaking something, it can be cheaper to just bypass it. And that's also true for public key infrastructure bugs, for implementation flaws. Rather than actually attacking TLS, you could just go to bypass things, for example, in terms of compression oracles or downgrade attacks. So instead of attacking something related to TLS 1.2, I might before that just try to downgrade the connection to something insecure. And you should also, especially regarding compression attacks, this should show you that if an attacker can guess only one byte here, he might eventually figure out some secrets. The same thing like with the Heartbleed attack, this enabled an attacker to read out, for example, 64 kilobyte of data sequentially, not only 64, but 64 kilobytes in one request. This can also already be enough so that confidential or sensitive data is leaked. And you should definitely make sure that your browsers, and if you own a web server, that it's configured to use secure ciphers, because otherwise there is a high chance or there's a potential ability that someone might just downgrade your communication. So to try what your browser is susceptible, whether, for example, the example of Superfish was just a placative example, but this happened multiple times with different certificates. On this website, which I've shown you last time already, BadSSL, they also include tests for such incidents related to such certificates. You see, for example, Dell was affected by this even twice. And if for example, in your case, on your computer, such as a Superfish certificate was installed, then you would actually see the result of this website, and you'd have a severe problem. So feel free to try this to see if your browser or your system is actually susceptible to this. I think not, because this is already around for quite some time. But as already said, chances are very high that if you're using, for example, the SS, Kaspersky, Avira, that they actually break your communication. So check out your certificate manager on your computer, in Firefox or Windows, especially to see if you have a certificate authority installed that seems fishy to you. And if you're uncertain, deactivate it, delete it, if you're really sure to delete it, or just Google it to find out who is behind there. As already mentioned, there are at least 46 countries that run their own CAs, probably you do not trust all these countries, or you do not want to trust all these countries. And last before not least, I know there's already a lot of content, but this is something on another layer, something easier. So there's also covered the entire communication to a server. Let's have a quick look now on DNS security. So why? I already outlined this in the very beginning, because in order to reach a server via TLS, we first usually resolve from a host name to an IP address using DNS. And DNS also suffers from some problems. So sometimes you probably don't think, well, users might not accept my certificate. As an attacker, you think, well, chances are there that users will say, oh, I get a certificate warning, I do not accept this. Then an attacker might just hook into DNS and try to bring the user to another server. In this case, an attack named cache poisoning. You trick the user into so that a host name resolves to another IP address. For example, how you could attack such servers? You'd, for example, what would be possible is a denial of service attack. You make it unavailable. What happens if a server can no longer resolve from domain names to IP addresses? The host will be unreachable. And that's been very popular in the past, and actually still is. If you want, it happened that, for example, someone wanted to press out money of someone and says, I make your website unreachable unless you pay me something. And one way to, if you don't do it, an attacker doesn't even have to attack the web server. By just making the DNS resolver, the name servers, unavailable, users will no longer be able to retrieve the correct IP address. Very often, it already happened in the past, that DNS was used for an amplification attack. In other words, attackers sent a tiny query to a DNS server. The response was large, but it didn't reach the person who queried it, but it went to another website. I'm going to show this to an example now. Or, as I already said, it can be that the user connects to a wrong destination IP address. So, just to illustrate this, for example, attackers quite some time ago produced an amplification attack that produced 300 gigabytes of traffic. And of course, this doesn't originate from just one computer. It's not one DNS server, for example, one server that's been used for that. But how can this actually work? It works by amplifying the bandwidth you use. So a lot of protocols like ICMP or UDP, they are stateless. There is no handshake involved. You send a request there, you specify the source IP address, the destination IP address, source port, destination port, but as a stateless message. So the next request is completely independent of the previous one. So what you could do, you could just send a packet to a server where you spoof the source IP address. So you ask, for example, a DNS server. DNS works on port 53 via UDP. You send a request, for example, give me all the IP addresses, so all the zone records you have. And as the IP address, as the promoted source, the spoofed source, I'm setting, for example, the IP address of some target server I'd like to target, where I'd like to do a denial of service attack. So if you do this in a clever way, you achieve that the response is significantly larger than the request. So in other words, for example, you say, give me all the A records of a certain domain, and the response you get is a huge list containing multiple kilobytes, or you could actually stress the DNS servers to send you a lot of data there. And if you do this in a distributed way, not only with one server, but with a couple of them, for example, an attacker sends 60 bytes of query and the response has almost 3 kilobytes, there's an amplification factor of 60. So if an attacker would actually just send such spoofed packets with 100 megabit, which is highly plausible nowadays that you send out packets with that bandwidth, it will produce responses with 5 gigabits. According to this measurement. So depending on what query and what response you get, it might be by far higher. And in the past, also in Austria, it happened a few times that, for example, the airport of Vienna, Schwechat, was unavailable, or some ministries, exactly because of such attacks. They are very easy to craft, they are very cheap, and DNS is only one example. You can also use, I think I showed this 2 weeks ago, or in 2 lectures before that, using Memcache. Memcache works the same way. We also had, remember, or it was the first time, yeah, the UDP reflection attack. This is basically the same thing, but especially with DNS there is such an amplification attack possible. In other words, the attacker can multiply the attack bandwidth. What can also happen is that you go to, for example, to a restaurant or cafe, and the problem is that you at some point will need a server that resolves domain names to IP addresses. And usually, in most settings, you take the servers, the DNS servers, you learned via DHCP. So let's say you go to a cafe. Of course, you don't manually configure the computer with an IP address. You just retrieve it automatically via DHCP. So in other words, you implicitly trust the server. And by implicitly trusting the server, it can serve you any reply it wants. So you can, if you request Google.at, you can retrieve any response, and you cannot really verify it. So something you've definitely got in touch with that already is if you went to, for example, to a hotel room, try to use the internet prior to authenticating. And a lot of hotels nowadays use so-called captive portals. So let's say you go to some domain, and the first thing that happens is that you see some login screen, and then you have to authenticate. So they actually do exactly this. If you're within such a hotel or an airplane, for example, and they're using such a captive portal, hotspot login page, then, or even McDonald's, yeah, they're also using this. They are just try to ping some arbitrary website, and what you will see is the IP address of the captive portal. This is how they bring you to that page, essentially. So how can you know you get the right response? And in fact, for an attacker, it's easy to trick someone into using the wrong IP address for a certain domain. This is then called cache poisoning. So for example, assume you as an attacker, you control the DNS zone evil.at, and someone requests wants to see the IP address of the domain. For example, because you send an email to someone that includes an image from that domain. What your email application, your email program does, it tries to resolve the domain in order to show the image. So in other words, to get the IP address. So if the DNS server is controlled by an attacker, it might be that you request the A record, in other words, the IPv4 address of the domain. You get an answer from the server with the desired IP address, and in addition, you get an IP address for another domain. So for example, in this case, the attacker's DNS server said the name servers responsible for evil.at are NS1 evil.at and Google.at, but by the way, in case you didn't know yet, you find Google.at here on that IP address. And since caching is a very important principle with DNS, well, DNS resolvers will simply memorize this IP address as being associated with Google.at. In other words, the next time you go to Google.at, your browser will use that IP address, unless your DNS resolver is clever enough to recognize this. So how do you get a victim to look up an attacker's domain? For example, send an email, or you can also trick a server into that. For example, you connect to a server via SMTP, and then you send hello, and then your domain name. What your server would immediately do is figure out the IP address and see whether it's blocked, for example, for spam filtering. And while the server resolves this IP address, it will also learn this tainted record or the tainted IP mapping. What can we do against this? Most of these attack scenarios, like forge and manipulated DNS data, use an extension that's called DNSSEC. And I won't go into detail here on DNSSEC. DNSSEC is not so easy to explain in just a few minutes, but what you should memorize of that is it's a chain of trust between all involved DNS servers, or name servers actually used to that are responsible for zones. So in other words, similar to these certificate chains which we have with TLS, DNSSEC builds such chains between DNS servers. And the idea is that if a domain name server, so a domain name server managing a zone, managing such a mapping, like in this case here for Evilater, if this server has DNSSEC enabled, then it will sign its answers cryptographically. So it will use an RFA key, and then using the DNS resolvers that see this signature will use a public key to verify who signed this and whether the response is tainted or not. So the idea is, of course, that the content cannot be modified, that it cannot be manipulated or forged, and that it shouldn't be possible that, for example, an attacker attaches this here, or that if you go to Google.at, that you will get to another IP address as the one you have requested. The problem is, with DNSSEC, everyone would have to use it. So that all the DNS servers would have to support it, and there must not be any other options other than using. So DNSSEC would have to be the primary one and the default case. In fact, DNSSEC is around for 10 years or more, and while it's been used by at least some websites, some servers, it's probably as distributed or a bit more than public key pinning. So not really widely deployed, and this ultimately leads to the consequence that man in the middle is still very often still very successful, and it's still in most settings possible for the attacker to redirect you to fake records. Yeah, so that gave you an overview about TLS, and also something you need beforehand before actually connecting to a TLS server from a DNS layer. From my side, that's all. The next event where we'll see each other is the lecture exam at the end of January. And next week there will still be Maria, and Maria will recap the most essential things from the lecture, and also give you an idea about what to expect from the exam. All right, I hope you enjoyed it. To get a better idea, I know this was a lot of content. To get a better idea about a better feeling about cross-site scripting, for example, HSTS, these attack vectors, cipher seeds, and so on, I strongly recommend you to try this out. In the slides, there are a lot of links to websites that enable you to try out how your browser reacts to different things, how your browser reacts to cipher suites, what cipher suites are supported on your computer, what certificate authorities you trust. So to get a feeling about all that, try it out. By trying it out, you will memorize it better, and it will be easier for you to explain what it works, what impact it has if certain condition is given on what happens by this and that. Other than that, in case there are any exams, of course, you will any questions, you're of course very welcome to always ask them, either in Discord or email. And I hope you enjoyed these sessions about network security. Next time there will be Maria again, and then the exam. So today there are no questions in the YouTube chat. Feel free to ask them later on if you like. So that's all from my side. See you at the exam.